Alrighty, so today we looked at topic 10.2, getting into functional group chemistry. This is where we start looking at the different types of reactions that the different functional groups can do and how those reactions take place. We're looking specifically at alkanes, alkenes, alcohols, halogenoalkanes, and benzene, and the polymers we'll look at through alkenes. Today we only made it through the first half of alkenes, so that's all this video will talk about, obviously. So talking about alkanes, right, we remembered that alkanes are saturated hydrocarbons. They have no multiple bonds, just carbon and hydrogen. And remember, they're going to be really non-reactive. The carbon-carbon and carbon-hydrogen bonds are super strong, high bond enthalpy. It's all super duper stable. Like alkanes just don't want to do anything. So the only two reactions that they're going to do are two very aggressive reactions. They can do combustion reactions and they can do substitution reactions via that free radical mechanism. So looking first at combustion reactions, remember we're now looking beyond the generic combustion reaction that we learned earlier on where we just produce CO2 and water. And we see that that is just under ideal circumstances, right? With excess oxygen, that's the reaction we'll have, and that gives us complete combustion. But in reality, there's going to be limited amounts of oxygen and varying amounts of oxygen. So you can also have two other incomplete combustion reactions yielding CO, carbon monoxide, or just solid carbon particulates. And in reality, when something is burning, unless you're really forcing excess oxygen, you're going to probably get a combination of all of these products. So also, we want to note that all of these products of combustion have a negative impact on the environment. Carbon dioxide and water are both going to be greenhouse gases, right, contributing to climate change. Carbon monoxide is toxic. And then remember, the carbon particulates, they're just really bad for you. Our body is not meant to handle these solid chunks of stuff. Okay, I'm going to have to just redo this because, all right, never mind, we get to keep going. So looking at combustion reactions, right, so all of these are going to produce nasty stuff. Don't smoke. That was the moral of the story with the carbon particulates and Industrial Revolution, right? We talked about all that stuff. Good. Moving on. So then we looked at the good stuff. So let me kind of zoom. Oh, shoot skis. Let me not zoom. Let me zoom with that. There we go. All right, so the second type we're going to look at is our substitution reactions, right? And these are going to be halogenation, right? We're going to, substitution meaning something takes the place of hydrogen. And for alkanes, free radical halides are going to be what does this. So a free radical, remember, is an atom that's been separated from its bond via homolytic fission, meaning the bonds split even-steven down the middle, producing two radicals, each one keeping its own electron. So each atom now has one unpaired electron. So if you were to homolytically split chlorine, you would get two chlorine free radicals. And a generic example for what you would see in your substitution reaction, you have the chloride radical attacking your ethane in this example, producing chloroethane, and then the hydrogen radical. That would be an example of a propagation reaction, right? So as we are looking into the details of our reactions, we're seeing that the mechanism goes through a radical chain reaction with three basic steps: initiation, propagation, and termination. So remember, the initiation is just where you create the radical. Smack the chlorine atom with some UV light, it'll break it in half, homolytic fission, creating the two radicals. Then your propagation steps, those are any step where you start and end the reaction with a radical. So like we said, this is just a mixing pot of crazy free radical wildness until it ends. And it ends with that termination step when any two free radicals meet and form a bond, right? So in the end, after this reaction, you are going to have a mixture of any and all possible products. The only way to direct this reaction or to have some semblance of control is to deal with the ratios that you have in the beginning. Do you put a lot of chlorine in or a little bit of chlorine in and stuff like that, and how long you let it go if there's a way you can quench it, which there really isn't. So yeah, really not a lot of control. Remember the melee. Everyone fighting for themselves, last man standing wins, that style. It is a crazy, crazy world of radical reactions throughout that propagation portion. And then that was it. That's all that alkanes can do. You can burn them, and you can just bludgeon them with free radicals, and that's pretty much it. Then, blank page. Then we talked about alkenes, right? And alkenes are now unsaturated hydrocarbons. So we are still looking at just carbon and hydrogen, but now we have a double bond. And that double bond allows us to to have some activity, to have some reactions happening. So notice we talked about double bonds and how a double bond is formed by a single bond, the sigma bond, which is what all single bonds are, and then the double part is a pi bond over top, and that's that weird weaker sideways overlap of the p orbitals. And remember, that second part, the pi bond, is weaker. That's where reactions are going to happen. They're going to happen at that pi bond. Also, we see that whenever you have a double bond, you now have that trigonal planar geometry around the carbons. Again, because pi bonds are weaker than sigma bonds, those are easier to break, and that's where those reactions will happen. So we will be looking at two reaction types here, addition reactions and polymerization reactions. Today, we stopped after addition reactions. So let's look at those, and then we'll be done. So for our addition reactions, remember they're all the same. You're taking some little molecule, hydrogen, chlorine, HCl, water, something really little, and adding it across your double bond. One part goes to one of the carbons, the other part goes to the other carbon, eliminating that double bond in the process. So adding H2, that is called hydrogenation, right? You use specific nickel catalysts, warmer temperatures, and you're just turning an alkene into an alkane. You are saturating your alkene. This, again, they would do industrially for hydrogenating oils to make margarine, right? Adding halogens, right? We could create a dihalogenated compound by adding a halogen. This is called halogenation. Again, we just add that Cl2 molecule across the double bond, one chlorine on each of the carbons. We would create 1,2-dichloroethane from our ethene. Again, each of these is adding across that double bond, one part on one carbon, the other part on the other. Then we could add hydrogen halides, right, like HCl. And again, one goes to one side, the other one goes to the other side. And these would also be halogenations, but this time we're creating just a monohalogenated compound. So only one halogen gets added because the other one is a hydrogen. So here we would turn ethene into 1-chloroethane. And the last one we looked at was dealing with adding water, and this is called a hydration. Should make sense. And again, we're using concentrated sulfuric acid here as a catalyst and doing it with heat, specifically steam. And this time we're producing an alcohol. This is a really important industrial reaction, producing ethanol as a solvent. Ethanol is used extensively in all kinds of industries as a solvent. So being able to make this quickly and cheaply is a really big benefit. So first we take our alkene, we add in our acid catalyst, and it starts the reaction, and then the water comes in, kicks out the extra acid part, adding in the OH, you get hydrogen on one side, OH on the other. You should know these two steps, but for the big picture, you can just think about water adding across the double bond. One carbon gets the hydrogen, the other carbon gets an OH, and then you're pretty much good to go. And that's it. So, good luck, and I hope that this all goes well. I'll see you on Monday. Please don't forget to turn in your isomer modeling projects and be doing your homework, be doing your work. We have a quiz on Monday. All right, see you later.